Okay, welcome back everyone. This video is called Graphs of Functions. And what we're going to do in this video is bring you from the more abstract land we had in the last video, where I convinced you that a function was something called f from a to b, which was a rule which took something in an arbitrary set A and transformed it via a crazy machine into something in an arbitrary set B. That was somehow our picture of a function. Here's A, comes through, here's f of a, and it lands in here. On the other hand, you probably also have a picture of a function in your mind which looks like what's over here on the big screen, namely this line here or this blue curve here. What those actually are graphs of functions. Those are graphs of functions which happen to be from the set, the real line, to the set, the real line. And the point of today's video is to convince you of that and to tell you about the difference between a graph of a function and the function itself, as well as to build some important vocabulary for later. Okay, let's jump right in. So suppose we have a function f from the real line to the real line. So here's a copy of the real line. Here's a copy of the real line, thought of as sets. Here's our little conveyor belt. Here's the machine, that is the function. Who knows what's going on in there. And here's the conveyor belt coming out. And in some sense, every single real number, x, comes into the machine, moves in, some stuff happens to it, and it comes out as f of x. And it lands over here. That's still the same picture, it's still valid. The problem is, as we saw before in the previous module, there's a ridiculously large infinite number of real numbers. And so, unlike a function from a finite set to a finite set, we can't just specify what it happens. We can't say that f of 1 equals Apple, f of 2 equals Daniel Egger, because there are infinitely many inputs. So usually, when we define a function from the real line to the real line, we have to give you a formula. So for example, you might see a formula like f of x equals 2x minus 1. What this is, so this is a formula. This is a rule that tells you how to operate the machine. Any input you give the machine, it tells you how to make the output. So for example, if 1 comes in, we know that f of 1, follow the rule, plug in 1 for x, 2 times 1 minus 1, that turns out to be equal to 2 times 1 minus 1 is 1. If we plug in 0, f of 0 equals 2 times 0 minus 1 is minus 1. And if we plug in a real number, which is not an integer, like 5.1, we get 2 times 5.1 minus 1 is 10.2 minus 1. Never good to do arithmetic in public, so I'm doing it like this, equals 9.2. And that's the point. That's the whole idea of the function. And you can have more complicated formulas. So for example, we could have g of x equals the absolute value of x, which we saw before, right? That's a formula which is often given by cases. This is equal to x if x is greater than or equal to 0, and minus x if x is less than 0. In both cases, both f and g here, are functions. They take input values x, they spit out f of x or g of x. In this case, you just have a formula for how to do it. Okay, so what? What's the point of a graph? Well, what's the correspondence between a graph and what we saw? So let's draw what you all know is the graph of the expression y equals 2x minus 1. We saw before how to plot the equation of a line. So there's y-intercept minus 1, always good to review. Slope is 2, so it goes about like that. So this symbol here, this is actually not the function. This is the graph of the function. This is the graph of the function f from r to r, whose formula is f of x equals 2x minus 1. Now what's the point about that distinction? But this is a nice visual picture. This allows you to depict all input-output pairs at once. For example, if x equals 0, I look at 0 and then I sort of think about where 0 goes until I meet the graph. And that point there, that's the point 0, comma f of 0, which we know is equal to 0, comma minus 1. If I say take the point 5.1, which is about there, and I look till it meets the graph, there it is. That's the point 5.1, comma f of 5.1. Okay, so in general, if, let's say, g is a function from R to R, the graph of g, very important concept here, is a set of points in the plane. So let's give it a name in the set. Let's call it graph of g. This is equal to the set of all points x comma y in R2 such that y is equal to g of x. And that's really the important distinction. It's a visual way of drawing the graph. Let's see some examples. So for example, let's draw our friend. Suppose g of x is the absolute value of x. Let's draw the graph. We already know that g of x is equal to x if x is greater than or equal to 0, and minus x if x is less than 0. It turns out that graph looks like this. You've probably seen that before. Often people will write then y equals absolute value of x here. What that's telling you is that every single point on this graph, the y-coordinate is equal to the absolute value of the x-coordinate. So in other words, if this is 2, the y-coordinate there is 2, which is the absolute value of 2. This is in fact the point 2, comma, the absolute value of 2. On the other hand, if I take minus 2, and I look at the y-coordinate, that's the absolute value of minus 2. So this point here is minus 2, comma, the absolute value of minus 2. And that's the idea of a graph. Okay, let's do one more example. Suppose h of x is equal to x squared. That's one of the things we saw at the very beginning. So let's draw our set of axes. And one of the things we're going to learn here is how to graph a function if you don't know what the graph looks like. For the other two, I was sort of cheating. There's no magic bullet here. There's no tried and true answer. Really, often what you do is test out a bunch of input and output pairs, see a pattern, and then try and draw a curve through it. The astute listeners among you will realize that's exactly what you do in supervised learning. You try to figure out what the function is going to look like by querying it, by asking a few inputs and seeing what the outputs are. So let's make, for example, a table. Here's x, here's h of x, and let's figure out a table. So if x equals 0, then h of x would be 0 squared equals 0. So let's plot the point 0, 0 on the graph. If x equals 1, then h of x is 1 squared equals 1. So let's plot the point 1, 1 on the graph. If x equals 2, then 2 squared equals 4. So let's plot the point 2, 4. 3 squared equals 9. And we're getting way up there, so somehow it looks like a curve going up like that. Let's try some negative numbers. Negative 1, we know that negative 1 squared equals 1. And pretty soon we're going to see a pattern of symmetry like that. And that's about what the graph of y equals x squared looks like. That's really how you graph functions if you don't know what they're supposed to look like. In a later video, you're going to learn a bunch of patterns of what linear functions look like, what quadratic functions like this one look like, what cubic functions look like, what exponential functions look like, and things like that. We're just going to close this video now by telling you something important called the vertical line test. And to illustrate what that really gives you, let me give you an example. I'm going to draw 3 curves in the plane, and only one of them is actually a function, a graph of a function. There's one guy. There's another one. And let's choose another color. Let's try yellow. Let's take a third graph, like this. Okay, so those are 3 purported graphs. Here's an interesting fact. Red could be a graph of a function. Red could be the graph of, say, y equals x minus 1. Blue could be the graph of a function. Even if we can't think of a formula, that could certainly be a graph. here's the wonderful fact. Yellow cannot be the graph of a function. There is no function whose graph is yellow. If you think a little bit about it, you'll see why. It violates something called the vertical line test. Namely, if I draw a vertical line, I can find a vertical line which hits the graph at two different points. Why is that a problem? Well, if this little point here is x, in essence I'm being proposed two different things for the value of the yellow function at x. There's that one and there's that one. And that's illegal, right? Remember, a function is a rule which takes one of the things in a set and assigns it to an element in the other set. There can't be any ambiguity. That's not the case with any of these other graphs, right? If I draw a vertical line here, it intersects the red guy in exactly one point and intersects the blue guy in exactly one point. So if this is the point x, I want to know what's the red function value of x? There it is. What's the blue function value of x? There it is. Any other vertical line, same exact thing. Intersects the red point at one point, so there's x, there's the red value of x, there's the blue value of x. There's that ambiguity with yellow. So let's actually write down what the vertical line test says. Any vertical line intersects the graph of a function once. If it intersects it more than once, we violate things here. Okay, that concludes this video.